So you know how if you draw two axes on some paper you get a graph? Usually one is named x and the other y, and we call it an xy graph. Well, in physics we can create a graph where one axis plots time and the other space. A space-time graph, if you will. On it, you can very easily see the movement of an object in one direction. Usually, we call these graphs space-time diagrams, and the tracked motion of an object over time is its world line. So if you see your friend somehow running at half the speed of light for 5 seconds, you would plot their motion like this, assuming they stop after 5 seconds. Normally in physics, we would study this motion, but in the mystic world of relativity, we study how this motion looks from different points of view. In a sense, we try to view the world through other people's eyes, and to do that, we would somehow have to make them appear to be stationary. But how would I do this? Well, one way is to use something in mathematics called a shear transformation. One of two important concepts to realize is if you see your friend moving away from you, in their perspective, you are moving away from them, but in the opposite direction. And if we change to their perspective using a shear transformation, your friend sees you moving at half the speed of light away from them. However, this transformation changes all velocities. This becomes problematic when you're introduced to the second important concept. The speed of light is always the same for all perspectives. This means that 1. Shear transformations in physics are wrong, and 2. Since keeping the times same for both you and your friend end up in varying speeds of light, the simple act of moving must affect time. Luckily, something called Lorentz transformations fix this. Through some complicated maths, we can see that this is, in fact, what happens. Time slows down to keep the speed of light the same for your friend. Using a program called Desmos, you can easily visualize this. As you change to your friend's perspective, your time intervals rotate and squish together, showing you that for them, your seconds happen faster than their seconds. Keep in mind, this all happens to preserve the speed of light, and consequently, time dilates. Similarly, there's another such phenomenon that happens because of the squeezing and rotating of your time intervals. Let's say there's a stranger in front of your friend that also happened to be running at half the speed of light for 5 seconds. You see both your friend and the stranger stop simultaneously. When you change to your friend's perspective, they see that the stranger stops before them, and if we move them farther apart from your friend, he stops sooner and sooner. This is because of the rotation of your time intervals, and as a result, no two people traveling with respect to each other can agree on the simultaneity of two events. Along with time, your space intervals also rotates and squeezes, which causes something called length contraction. If I take your friend and stretch them 600 million meters and then throw them at half the speed of light, as they move, you will see them become shorter. And as you can see, this does in fact happen when you look at the graph. When you measure him in your perspective, you get about 520 million meters. But if you ask what they measured, they'll tell you about 600 million. So who's right? It's kind of the same thing as adding 2 plus 2. You see it equaling 4, while I, the intellect, see it as being fish. We are both right in our own respects because with 2 2's you can draw a fish, while when you add them, you get 4. The answer you get from your own perspective is the correct one, while your friend's is too.